So we're going to be doing questions on concentration, but before we get into that, let's discuss how to solve most chemistry problems. First, you identify what the question is asking for. It's the easiest part of the question to identify. What are you being asked for? And especially, what are the useful units of that answer? Because the units will provide a guidepost, a roadmap to solving the problem if you use useful units. So survey the given information and if necessary rewrite units as useful units. By useful units I mean units that can be used in dimensional analysis. For example, instead of molarity, which is a perfectly great unit, but you can't use a capital M or the word molarity in dimensional analysis. You'd need to convert it into the definition of molarity, which is moles of solute per liter of solution. That can be used in dimensional analysis. And then work towards the units of the answer by multiplying or dividing as necessary to cancel out the unwanted units and end up with the units of the answer. Now let's talk about the units of concentration of a solution. There are four usual ones that we use in chemistry. The one you're most familiar with so far is molarity. That's moles of solute per liter of solution. There's also percentage. That would be parts of solute per 100 total parts, but usually as a weight or mass ratio, grams of solute per 100 grams of solution. If we're actually given a percentage, a solution is 5% sodium chloride, we'd express it using this notation, 5 grams of NaCl per 100 grams of solution. So if we're given the percentage, we express it in this useful unit. If we're calculating percentage, we calculate the grams of solute, we calculate the grams of solution, we divide one by the other and multiply by 100. That'll give us the percentage of that solution. There's also molality, used mostly in calculations involving colligative properties, such as freezing point depression or boiling point elevation. We use it because it's independent of temperature, and we have moles of solute per kilograms of solvent. This is quite a departure from molarity and percent, where we have solution in the denominator. Here with molality, we have just the kilograms of solvent. Finally, another unit useful in colligative property calculations is mole fractions. That would be the moles of solute divided by the total moles. That would be the mole fraction of the solute, or the mole fraction of the solvent. So here we go. Calculate the molarity of the solution formed when 34 grams of sodium chloride is dissolved to make 345 milliliters of solution. So pause the playback, try to do the problem, and then come back and we'll discuss the answer. Pause. Okay, so the goal is molarity here, and the useful unit is moles of solute per liter of solution. That's what we want to end up with. We take our 34 grams of sodium chloride, convert it to moles with the molar mass, 0.58, and then divide it by the volume, 345 milliliters, or 0.345 liters. Then we end up with moles per liter, which turns out to be 1.7 molar. All right, let's try another one. How many liters of 0.52 molar NaOH contains 72 grams NaOH? Pause and come back and we'll discuss it. Okay, the unit of the answer is liters. That's our goal. And 0.52 molar NaOH is 0.52 moles NaOH per liter of solution. So how do we get moles of NaOH to cancel out and leave our answer in terms of liters? Well, we convert grams of NaOH to moles and then invert the molarity to put 0.52 moles of NaOH in the denominator so that moles NaOH cancel with moles NaOH, and the units we're left with is 1 liter of solution. And we divide it out, 3.45 liters. Now let's try this one. Pause your playback and come back and we'll discuss it. So on this we're being asked for the percent by weight of potassium chloride for the solution. And the useful units for percentage is grams of KCl, in this case, divided by grams of solution times 100. That's how you calculate percentage. So what we do is find the total mass of the solution, 27 grams KCl plus 93 grams water, 120 grams of solution, divide that into 27 grams of KCl, and we get 23%. Pause your playback and try this one. The units of the answer is grams of water. How many grams of water would you add? So what do we have? 250 grams of NaOH and a 9.6% solution. Turning 9.6% NaOH into useful units, that's 9.6 grams NaOH per 100 grams of solution. Applying that to the 250 grams we're given of NaOH and arranging it so grams NaOH will cancel with grams NaOH and leave us with grams of solution, we end up inverting the percentage and we get 2,604 grams of solution. We subtract the grams of NaOH to give us the grams of water that we have to add to get that percentage. So now try this one, pause your playback, and come back. Okay, we're being asked for molarity of ammonia, which is moles of ammonia per liter of solution. We're given 35 grams of NH3, and we convert that into moles of NH3, and we add the grams of NH3 to the grams of water that we're given to get the grams of solution. We use density to convert from grams of solution to milliliters of solution by dividing by the density, 139.2 milliliters of solution. So now we divide our moles of NH3 by the liters of solution that we've just calculated to get a 15 molar solution of ammonia. Okay, let's try this one. What is the molality of 1.5 grams of sugar mixed with 490 grams of water? I'll pause the playback and you try it and then come back and we'll discuss it. Okay, the goal is molality, and we must know how molality is defined. Moles of solute, in this case sugar, per kilograms of solvent. So we take our grams of sugar, divide by the molar mass to get the moles of sugar, and take the grams of water and divide by 1,000 to get kilograms of water, divide one by the other, and bingo, 0.017 molal. Here's another one. You try to do it and we'll come back. How many moles of calcium nitrate are in a 2.2 molal solution of calcium nitrate with the mass of the water solvent given? So the units of the answer we want is moles of calcium nitrate, and 2.2 molal calcium nitrate is 2.2 moles of calcium nitrate per 1,000 grams of water, 1 kilogram of water. Those are the useful units. So very easy. Multiply the molality by 38 grams and you'll get moles of calcium nitrate. And that's what you're looking for, 0.084 moles of calcium nitrate. So here's another one. Put it on pause, you try it, and come back and we'll discuss it. Okay, we've got 18 grams of potassium chloride added to 89 grams of water. We want the mole fraction of potassium chloride, mole fraction of the solute. The useful unit of mole fraction of the solute is moles of potassium chloride divided by total moles, which is moles of potassium chloride plus moles of water. We're given grams of potassium chloride. Use molar mass to convert to moles of potassium chloride. Use the molar mass of water to convert to moles of water. Add them together to get total moles. Divide the moles of potassium chloride by the moles of water. Bingo, there's your answer, 0.047. Okay, read this question, put it on pause, you try it, and then come back. We'll discuss the answer. The goal here is to find the molarity of the sodium chloride solution. The useful unit of molarity is moles of solute, sodium chloride, per liter of solution. You're starting with molality of sodium chloride, though, and that's defined as moles of sodium chloride per kilogram of water. So you're essentially given the moles, the numerator of what you're seeking, the moles of sodium chloride. And task here is to convert the 1 kilogram of water somehow into liters of solution. And we're given the density, 1.03 grams per milliliter. That's the density of the solution. Grams of solution divided by milliliters of solution. So we have to find the total mass of the solution, so we can use density to convert to milliliters and then to liters. So 0.47 moles of sodium chloride, use the molar mass to convert to grams of sodium chloride. Add that to the 1,000 grams of water, which is the denominator in molality, right? 1 kilogram, 1,000 grams of water. Add them together, we get 1,027.47 grams of solution. Now we use the density, dividing by 1.03 to convert into liters of solution. Divide the moles by the liters for our answer, 0.47. Okay, you know the drill. Try this problem and come back and we'll discuss the answer. Okay, we are trying to find percent, that's our goal, which is the mass of sodium chloride over the total mass times 100. We're starting from molality, 0.47 mol sodium chloride, which is 0.47 moles of NaCl per kilogram or 1,000 grams of water. So first, since we're doing a mass or weight percentage, we convert the moles NaCl into grams NaCl by multiplying by the molar mass. And we take our kilograms of water and convert it to grams, 1,000 grams, and add it to the grams of sodium chloride. So now we have the total mass. So divide the grams of sodium chloride by the total mass times 100, and we get 2.7%. Okay, let's try this little more complicated question. Put it on pause, try it, and come back and we'll discuss it. So, the mole fraction of sodium chloride in an aqueous solution is 0.0036. What is the molarity of this solution? So our goal is molarity, which is moles of sodium chloride per liter of solution. We're starting with mole fraction of sodium chloride, which is 0.0036 moles of sodium chloride per 1 mole total of NaCl plus water. So it's important to realize that when you divide through by a ratio, the denominator becomes 1. So first we're going to find the moles of water by subtracting the moles of sodium chloride from the 1 total mole of water and sodium chloride, and we get 0.9964 moles of H2O. Now we're going to convert the moles of NaCl into grams by multiplying by the molar mass. It's 0.21 grams of NaCl. And we're going to convert the moles of H2O into grams of H2O by multiplying by its molar mass to give us 17.94 grams of H2O. We find the total mass by adding the two masses together of water and sodium chloride, 18.15 total mass of the solution. And now we can use the density of the solution, 1.06 grams per milliliter, by inverting it. So we're dividing by 1.06 grams of solution in the denominator and 1 milliliter or 0.001 liters of solution in the numerator to give us our volume of the solution, 0.01712 liters. Now simply divide the moles of NaCl by the liters of solution and we end up with the molarity. Okay, an aqueous solution is 3.8% sodium chloride. What is the mole fraction of sodium chloride? Pause it, you try it, and come back and we'll discuss it. So we're starting at 3.8%, And the useful unit there is 3.8 grams of sodium chloride per 100 grams of both sodium chloride and water. We want the mole fraction of sodium chloride, which is defined as the moles of sodium chloride divided by the total moles of sodium chloride in water. So we turn the 3.8 grams of sodium chloride into moles of sodium chloride. We take our 100 grams total sodium chloride in water and subtract from it the 3.8 grams of sodium chloride to leave us with 96.2 grams of water. And we convert those 96.2 grams of water into moles by dividing by the molar mass of water. So now we have the moles of sodium chloride, and in the denominator we add together the moles of sodium chloride and the moles of water to end up with 0.012 mole fraction sodium chloride. So here's a little more complicated question. To what volume should you dilute 48.5 milliliters of a 5.4 molar solution of potassium iodide so that 23.5 milliliters of the diluted solution contains 3.75 grams of potassium iodide? So you try it after pausing it and then come back and we'll discuss it. Okay, here we go. First of all, it's not so much this question is difficult, it's that the way the question is worded is a bit tricky. What we have here really is a dilution problem. And we'll talk about the simple formula for dilution problems. But first we have to translate the wording here to make it more obvious that it's a dilution problem. This is telling us the new molarity after dilution in a sneaky way. And that is by saying that 23.5 milliliters of the diluted solution contains 3.75 grams of potassium iodide. So what you have to do first is convert 23.5 milliliters and 3.75 grams of potassium iodide into the new molarity after dilution. And that's not so difficult. If you think about it, 3.75 grams potassium iodide, divide by the molar mass of potassium iodide. Now you have moles of potassium iodide, and divide those moles by the liters of solution, 23.5 milliliters or 0.0235 liters. So that's a molarity of 0.962. That's the new molarity after dilution. Now the formula for diluting a more concentrated solution to a more dilute solution is the old molarity times the old volume equals the new molarity times the new volume. And the reason this works, if you think about it, is when you dilute, what are you doing? You're just adding water, you're adding solvent, but you're not changing the number of moles of solute, in this case potassium iodide. That's going to stay the same. So the old molarity times the old volume will give the moles of potassium iodide, and the new molarity times the new volume is also going to give those same number of moles of potassium iodide, because you're not changing the moles of potassium iodide. That's why there's an equivalence here. So now it's pretty easy to set up. We take our old molarity, 5.4 molar, times 48.5 milliliters, and that's going to be the moles of potassium iodide in the more concentrated solution. And that's going to be equal, after dilution, to the new molarity, which we know to be 0.962 molar, times the new volume, which we're trying to find out. And if we solve for volume, by dividing this product by 0.962, we end up with 272 milliliters. So we dilute the 48.5 milliliters of 5.4 molar potassium iodide to a new volume of 272 milliliters. Okay, so here's the last one. Nitric acid is usually purchased in a concentrated form, which is 70.3% by mass and has a density of 1.41 grams per milliliter. How much concentrated solution, and by that we're asking for milliliters of this concentrated solution, would you take to prepare 1.15 liters of 0.110 molar by mixing with water. All right, pause it, you try it, then come back. Okay, here we go. First, figure the moles of nitric acid needed to make the diluted solution. And we simply multiply the molarity of the desired solution we want by 1.15 liters, the volume that we want, to get the moles of nitric acid, 0.1265 moles nitric acid. Now we convert those moles to grams of nitric acid by multiplying by nitric acid's molar mass, 63 grams per mole. We end up with 7.97 grams pure nitric acid. But we don't have pure nitric acid. We have 70.3% nitric acid. So we have to calculate the grams of 70.3% nitric acid that contains our desired 7.97 grams pure nitric acid. Do you understand why the units have to be explicit? If you take shortcuts here and don't put a full unit label down, you're denying yourself the roadmap to success. So 7.97 grams pure nitric acid, we divide that by 70.3 grams of pure nitric acid per 100 grams of 70.3% nitric acid, and that gives us 11.34 grams of the 70.3% nitric acid. Now we use density to convert those grams into milliliters by dividing by the density 1.41. We end up with 8.04 milliliters. So dilute 8.04 milliliters of the 70.3% nitric acid to a total volume of 1.51 liters. So that's it for this unit. The next unit is going to be colligative properties.